So thanks to the organizers for the possibility to stay here as a short-term visitor. I'm going to talk about general model theory done in type theory. So there are several general frameworks for models of type theory. For instance, categories with families, categories with attributes, contextual categories, etc. And they are all formulated in ordinary set theory, which then serves as the meta theory. Well, the types of the type theory may, however, be interpreted as objects of any kind of category we wish to consider. So this works very well for meta-mathematical results about type theory as a formal system. So, however, we would like to use model constructions inside type theory itself, and perhaps also to verify properties of the model with the help of proof assistants such as COC, which are then based on a type theoretical language. So it seems that we have to rethink how we formulate these models in a suitable language for type theory, and that is what I'm going to discuss in this talk. And in particular, I will look at the problem of formulating the Setoid model of type theory inside intentional type theory, which is an old problem. Okay. So yes, this is said. Yeah, there is one well-known Setoid model of type theory. That's Hoffman's model from his PhD thesis, which was built from the syntax and the judgment of intentional types theory, and was used to translate proofs made in extensional type theory into proofs in intentional type theory, and to prove certain conservativity results there. So regarding the modeling of type theory inside itself, some work has been done, by Dubier, for instance, Peter Dubier, who formulated a version of categories with families inside type theory, but there are quite difficult coherence problems to be solved. And another kind of modeling of type theory in itself is to put itself to make it closer to type theory itself, so that definitional equalities of type theory are interpreted as definitional equalities of type theory again. And there are examples by Per Martin Löv and others who have done this. But we want to really consider the classical structures, or as they would, like categories with attributes, which we shall concentrate on. How would they look inside of type theory? So what is a category with attributes? Well, that's a category with a terminal object, and this is thought of as the category of contexts and substitutions. So the terminal object is the empty context, and so the objects are the context, and the morphisms are the substitutions. We saw this yesterday also. Okay, and then it has a functor, which to each object here, context, assigns a set of types in that context, T of gamma. And the functor, the morphism part of it, it tells how the substitution act on these types. So we write, so if we have F here, substitution between B and gamma, T of F sigma is, the substitution applied to sigma then, by definition. So that's a completely abstract definition of substitution, and it's functorial then, of course. Okay, and to each type in a context, there is a new context, the context extension, which extends it by that particular type. And there is also a morphism that just projects the first terms into the original context. Okay. So that's the categories with attributes, and we have also to tell how these substitutions interact with context extensions. So this will be a pullback square of this kind. So here we have a context extension, we have an arbitrary substitution. Then there is a canonical pullback square of this form, where this becomes the projection of where we have to carry out the substitution, and this will be the last variable of it, so to say. So this is a pullback, and it should satisfy a number of functoriality properties. So if you put two such substitutions side by side, you have again a pullback, but you want to know that that pullback square actually comes from the canonical Schusen Q here, so and the P, and that's what this says. Right. Okay. So we have chosen here an algebraic formulation of categories with attributes, and it seems that the one that may be easiest to generalize. It doesn't mention set in more than one place really here, and that's the here. There is an equivalent version called categories with families, where you have to talk about families of sets as well. But here the elements appears actually as sections of these projections, rather than in the categories with families where they are given. Okay, so in set theory we could choose constructive set theory or some ordinary set theory. We could construct such as category with attributes from any set which contains a singleton set for the terminal object, and which is sigma closed. Well, this is kind of a regularity condition for a cardinal, for instance. So if you have any set in that one, and you have any function from the set into U, then this some set belongs to you here. So there are axioms like this in that guarantees that such sets exist in constructive set theory, and of course in set F. Yeah, and we can then take the category here to be the full subcategory of those sets with objects in this small universe. And well, then the families will be given by this. Well, it will be this functor, representable presheaf. So all the families will be bounded by U here. So right, and then the context extension is just the sigma in this case. Right, and the pullback diagram here will then take this easy to understand form. So you have the sigma here, the context extension, and what was this? Yes, it's the context extension where you have substituted F for this one, and these are just the projections. Yeah, and by assuming that this universe is closed under further constructions, one can verify type theoretic constructions like pi, W, identity types, and so on. I don't know that this has been written out in full or published at least. So, okay, so yeah, we have then sort of indirect model of if we like, extensional type theory. We could take, we could use CZF and Axel's model of CZF. That's a universe formed by W types in type theory, and so in principle we could formulate the whole theory of CWAs inside ZF, and then use the interpretation back to type theory to get our model. And well, actually that model has been formalized in Koch and Lego and many other proof assistants already. So in principle this would give us such a model, but maybe this is not the most satisfactory way of doing it. It's very indirect. Yeah, one can note that there is actually a full and faithful functor from the sets, the category of sets in CZF, in the CZF model, into Setoids. So yeah, you can extract it from it. But okay, we are interested in more direct interpretations.
Into Setoids in CZF?
No, in type theory. Okay, so what is Setoid? You probably know it. There are several things that are called Setoids in the literature, but I think this is the most common one. So in type theory, well, it goes back, of course, to all constructive mathematics as developed by Bishop. It's some kind of type together with an equivalence relation. And so there are, yeah. Now we are in type theory. We're describing what is the counterpart, best counterpart to sets in type theory.
So by equivalence relation, you mean arbitrary dependent?
It would be an arbitrary dependent type, depending on two elements, yes, and then you would have proof objects for showing symmetry, reflexivity, and transitivity, and so on. No further conditions on those, no. It's usual to keep this information along proof objects, but we omit them here for. Yeah. So it's a type with an equivalence relation, okay. And then we have functions, which are extensional functions. They respect the equality, and this is also given by a proof object, and all of this is formulated with pi types if you're careful. And we consider them equal if they are pointwise equal in the usual way. So, yeah.
Sorry, can you slow it down here, because this is because right now some things we're talking about here.
Yeah.
When you say we identify them, the pointwise equal, how do you perform that identification in type theory, since we're doing this now internally?
Well, you say that there exists a proof object of this thing here. So there is a term of this type, where this will become pi, and yeah, this is this relation that comes.
So that's the condition.
Yeah.
But then what do you mean by you identify them?
No, I don't mean. Then I don't mean we identify them. There are two different terms of, but it's the definition. It's the definition of it. Yeah.
Is that there exists a proof?
Right. Yes. Okay. So yeah, this becomes a category, as is well known, and so-called E category. I will come to that. It means that we don't care about the equality on objects, because there is a priori no good such notion, or well, there is one, but it will not give us a category. Okay, I'll come back to that. So it can be, of course, described in the same abstract way as the category of sets is described in constructive set theory or set theory. And so the properties of this category, that comes from the background type theory. And there are many results about this depending on the type theory, but it will be usually locally Cartesian closed category with or locally Cartesian closed pre-topos with some extra properties depending on what kind of inductive type you have and so on. Yeah.
Maybe you can give some literature on this, because this is the sort of thing that one often reads, but I have never seen a explicitly worked out proof, and I would like to understand how that could be. For example, if this could be a local Cartesian closed category when we have not really made these identifications. We've simply defined the notion of extensional by saying a certain type is an additive. So that, how does this give us a category which is really a local Cartesian closed category? I'm saying that somehow externally, if we make the pass to the quotient by identifying functions, function terms which are essentially equivalent, then we get an external category which we include the booklet that you proposed?
No, it will be an internal category, an e-category actually. So it's formulated very similarly to the standard way, but it's just we do not care about equality on objects. The slice categories are, they are the same basically. Yes, Setoids of morphism. That's right. So it will look actually. I will maybe come to some examples. So one paper where this is done is the one by myself and Erik Palmgren.
Yeah, that paper is very vague on exactly this point.
Okay.
That's why I'd like to hear precisely
Okay.
how it's supposed to work, because that's the one that everyone else refers to.
Yeah.
But then when you look at it, it goes by different so it's real precise.
Okay. I can.
That one refers to Huffman's thesis, and that's where the average.
Right. Okay. Yeah,
So
but
I
maybe
would like to know how this construction
maybe I can do it
works.
later on.
We do it later.
Okay. Yeah. So okay. So here's the E category. So which I. So what is an E category? Here it's a type of objects together with a Setoid of morphisms, right? And we have a composition which is an extensional function, which will satisfy the usual laws with respect to equality on each of those. And then we have an E functor. And the object part is just a function between the types. So it doesn't have to respect, there is no equality to respect actually. So it can just ignore that part. But it should be extensional on the morphisms. Right. So I could. No, it's up to equality of the that belongs to the corresponding. Well, there is no functorial law for that really. Right. Yeah. So what you do is, for a locally Cartesian closed category, you have this category here, and you can consider slice categories as should be all right. Okay, and what will this be? Its objects will be the arrows of from some object here to there. Okay. No, not equivalence clause. That's the difference from the standard one. So if the arrows, two objects are equal as arrows, they will only be isomorphic in this one. But that works out as expected. So you have a pullback functor there, and you can show that the right adjoints are given by the constructions of type theory, and they don't refer to the equality on objects at all. So. Okay, and then you show simply that this has co-equalizers, and that the sums are disjoint and so on. So it's not really hard to write down in even in Coq, I think. So.
Fair to say that it's a locally Cartesian closed E category?
Yes, it's an E category, of course. Yes. Right. Okay, so we will need to talk about also families of setoids here. So in type theory, this is of course the very fundamental object, and we want to interpret that in setoids. So we must ask, what are families of setoids? What is a family of setoids indexed by a setoid? Well, there are some choices. So we have an index setoid, and for each element of the setoid, this should be a setoid again. And if these are equal elements of the index, this should be equal in some sense. And well, here's the problem. We a priori don't have any other equality here than the definitional equality, or possibly we could have identity types. But yeah, anyway, we take equality here to be at least a bijection between them. And the bijection should be compatible with the proof objects. So one could think of two cases here. Either that will be independent, the bijection will be independent on this proof, and in this case we call it proof irrelevant. Or it may depend some way on P, on the proof.
And independent in exactly what sense? It depends on the existence of the proof.
Yeah, but if you have two, so independent means if you have two P and P prime, then those two will be extensionally equal functions. Right. Otherwise, we say it's proof relevant in some way. Okay, and for the proof irrelevant family, so this was actually a known thing from constructive texts on mathematics, this one. So if it's a proof, well, x equals x, then it should be the identity. And otherwise, it should satisfy this functorial law here. So if you go from x to y, y to z, it should be the same as going from x directly to r by any means. So, yeah. And from this, it follows that it's dependence, independence, as I stated it. So, in fact, one looks at this and sees that this corresponds to functors from the discrete category that comes from any E category. So, yeah, this is the analog of the set theoretic version here, right? So the objects of this E category are the elements of A, and the morphisms are the proofs of equality between two elements. And then you identify any two proofs. And this will correspond exactly to a functor. A functor from this one to Setoids will correspond exactly to the proof irrelevant families, which is quite easy to see. Yeah, and the proofs of transitivity and so on gives composition, etc. And it doesn't matter how we do these proofs, they will always be such, of course, since it's irrelevant. Right. So, yeah, one drawback of proof irrelevant families is that there are too few of them. So you will not have a proof irrelevant family for every family of type theory. So one could think that it's possible by considering identity types. So if you take family here and you consider the canonical equality on that, which would be identity, you get a setoid. And well, this is indexed by A here. And if you look at the two proofs that x are equal to x prime, for instance, then there is a way of going from bx to bx prime by substitution. That's the natural thing. Every proof object in an identity type gives rise to a substitution. And in fact, this gives us a functor, but it will be a functor from a groupoid that comes from the type A. So it will not be, it will be actually be a proof-relevant family unless we know something more about the underlying identity type here. So here's a small result about that. So if the type satisfies uniqueness of identity proofs, that is, if there are only one proof up to identity, well, that's equivalent to Streicher's axioms holds for A, right? And it's also equivalent to say that for any family over A, this B that I described will be proof irrelevant. So it tells us that this doesn't work very often well, we know that AP fails for, in general. One can show UEP for decidable types with decidable equality by what is called Hedberg's theorem. Okay, so they are quite a bit too few.
And particularly for representation of the universe.
Right, yes. So suppose we want to form a universe of or category of sets inside inside type theory. So one idea would be to use the Setoids and suppose we want to make an equality on that. It would be quite natural to use the only non-trivial equality that we have for types, namely the identity types. But that will actually not work unless we have one of these axioms. So just a note here how to make so if you have any proof irrelevant family, we may construct a category from that whose objects are the elements of the index set and whose arrows are triples, domain, codomain, and an extensional function. And then equality between two such will be that we require the domains and codomains to be equal, and that the unique mediating function here will give rise to a commuting diagram. And the proof elements comes in exactly when verifying that composition is extensional. Ordinary, no. An ordinary category will here be a category where you have a setoid of objects, right? Good point there. So.
Sorry, I'm missing something. Can the A-sharp with this Greek set
Yes. Right. So it's you define an E category, right? So this E category will have the objects, the type, okay, and this dimorphisms will be the equality relation between A and B, and okay, so it should have an equality relation, and we identify any two proofs of that. Any two proof objects that A is equal to B. Okay. So that will give us our A sharp. So it's we just say that the elements are related whenever. Yeah. Yeah, make a new setoid of it. Yeah, so it's very straightforward, actually. Okay, so what would happen if you take a proof-relevant family? Then you would have three objects like this, but they would have rather a groupoid structure. So this can, I don't know if it probably has a name, but this is a category object in some higher E category of groupoids. So if we look at this in the classical case, this would be a category object in the two category of groupoids or something like that. But okay, it's not comparable because we don't have that machinery yet. So. Okay, and this behaves a bit like the category setoids. It contains them, of course, some subcategory of setoids. It's almost category, but it seems very hard to work with. So it doesn't easily if this had worked, we could have used the original CWA definition by taking the category of sets, setoids, in the ordinary category of setoids. Okay, we can do that if we assume Streicher's axioms, but that is going beyond standard type theory, of course. So it seems that one has to reconstruct a universe of setoids to do this. And one way is, of course, to use set theoretic universe like Axel's model. But then again, it's not really setoids. Yeah. So we will redefine the notion of CWA. And henceforth, we will consider families of setoids to be the proof irrelevant ones. Those have nice properties in many ways. They come as the fibers of extensional functions and so on. So if you go back to this first, I'm not sure I can jump so fast here. So if you look at some of the original, so recall now we are looking at CWA. And we want to understand this with an E category here instead of an ordinary category. So we must not talk about equality of objects. But in fact, in some places, in these equations, if one just writes down those, one will see that we are actually requiring two kinds of equalities of objects. Okay, so let's go back to that. Domains and codomains, right? Yeah, I will. Okay, so here it is. Actually, these will be the upper corners of one of the equations. There's an upper corner of the other equation, of the pullback square, I should say. So, yeah. And furthermore, this one, which also depends on has a codomain. Yeah, that's okay. Yeah. So actually, this in the classical situation, it follows from the factoriality of T and requiring that object equality are respected in this way.
What is the equality between the capital A?
Yeah. Now I'm referring to the old definition. So it's the equality in the category.
Object equality in the category.
Yeah. Yeah.
But it was an E?
No, it's not an E category yet.
Oh, it's not.
Yeah. So now it's just an ordinary one. So let's see what we can make of this then. Yeah. So yeah, here's the slightly modified structure. So an E category with attributes, it looks about the same first. So we have an E category instead of a category. But we have an E functor from the contexts and substitutions into setoids and not sets. And then this assignment of a projection to any type over gamma, it becomes a small functor here. Right, so it assigns on the objects, it assigns a type, and here it assigns a projection. But we also must tell what happens when we have two equal types. Okay, I write this as delta here. Maybe I should write this as P. So these are the objects here, right? And we take the discrete category here, so it will be proof irrelevant in some way with the function. Yeah, proof irrelevant. Okay, and this is the slice E category that I indicated. Right.
It's like secretly making choices.
Yes. Yeah. Yeah, but type theoretically, that's not a problem.
Yeah,
Yeah.
Choices of what?
Of yeah, projections and given sigma we choose. Okay, so what does this functor mean here really? Okay, well, it says that for any proof object that these two types are equal in the context gamma, there is an isomorphism. Because the first category is all the morphisms are isomorphisms, so they will be an isomorphism that makes this triangle commute. So it's a kind of canonical coercion of the type sigma to sigma prime here. Okay, and since we use this hash construction, discrete construction, it will be independent of the proof object, so it doesn't matter, and it will be factorial, of course, also. So, yeah. Okay, so these kind of coercions will then appear in the equations. That makes it a bit more complicated. For any object here, you would have a morphism, the projections like this and the pullback. And now we can adjust our proof, our equations here by introducing these explicit coercions in some places here. So that will look like that. So I call them typed correcting morphisms. So and one can also see that these commutes with these projections in a sense also. So a question is whether all of these will commute with all of the operations in some suitable way, so as to make it easy to deal with. I don't know that, but it's a question. So anyway, these new ECWAs suggest us to introduce some judgments about types. So now we make a syntax for talking about these judgments. So sigma is a type in context gamma. That would be that sigma is a member of that. And the equality is, of course, equality in that one. So those were the easy ones. Right. Yeah. As mentioned, the elements of a type in a context, that will actually be a section of the corresponding projection here. So the elements will be the setoid of sections of the projections. So that's quite natural, right? And oops. And then we can see here that if we have how the coercion also works. So if you have a proof that these types are equal, then an object here is transported into this one by composition with a type coercion. Right. Yeah, and the slightly awkward part here is how do we interpret the membership judgment. So we have this as membership. So any types comes with an original type, the type it gets when it's first created. And then we can ask that it's a member of some other type. And this simply means that, well, the type, those types are related. And what is the quality of these two things then in a type? Well, they come with their special birth certificates or whatever you call it. Principal types, maybe. I'm not sure that's good terminology. Okay, so it means, well, they are members of this type in this sense, and there is a proof that those two are equal, and they are related in this way with the coercion. So that would be the meaning of that. And then you can justify these rules formally here, but of course this standing for pairs of an element with a principal type, and yeah, so they are immediately justified formally as judgments. Okay, and yeah, substitution into terms. Unlike categories with families, we have to make the substitution. It doesn't follow with the functor as in that case. So one has to construct the substitution of it into a term M here. And this is done using the pullback property of the square in a straightforward way. So we have to compose the term with F here, and look what is this one. And that will be the section then of the substituted. The section will be then the substituted terms. The substitution, we have only defined it for types so far. And that was given by the functor.
And so this we would have to do also before if we want a general substitution.
No, it follows from the way we have defined the elements as sections. Yeah. Whereas in categories of families, that would be included in the fact that we have a functor from this context category, contravariant functor, into the category of families. That would take care of that. So, but on the other hand, then we don't require this pullback diagram, but we have another condition. So that makes it a bit simpler, actually. So. Okay, and then we can check the stability under substitution. If you have an object in this sense, member of sigma, you take the substitution here, and you can compute using the diagram that this will actually be an element of that one. So we have this substitution rule as well, formally justified. Yeah, and one can go on to equalities, etc. This is slightly more complicated. Maybe I will skip this. But we have the expected rule also there. Okay, so we haven't said anything about type constructions in these CWAs. There are well, we should have pi types, of course. So here's the definition for a CWA. We introduce a pi, which should be this pi of sigma over tau over sigma here. So they have different types. This is the type in that context, and we can introduce the type there. Okay, and we have a lambda abstraction if we have a term. So now the term here, we abstract on some element of x in sigma there, and write it like that. And that should be an element of that type. And of course we have application, where we do the appropriate substitution in the target type. Okay, and then there are equations for these. Beta reduction, nothing special happens there. Pi substitution, this is how substitution distributes over pi. So we have this adjustment here, right? Lambda substitution, we also have to a bit more complicated, and application. Right, so those are the, yeah, so that was for the standard situation. And now if one just tries to type all this in the E case, we get a few of these deltas appearing in the coercions. So yeah, the first part is completely similar. But then comes lambda substitution. Okay, so I just put the types of those also here. So here appears again a coercion. And this is any proof. Well, there is a proof of it, so any proof will do. For application, we have two of them, one there and there. Yeah, I'm not sure this is the. There are many different ways of expressing them because these they are independent of the proof objects, and you can shift them from one side to another because they can be inverted and so on. So maybe there is one canonical good way of writing this down. But this is what you get when you look at the typing judgments. Okay. So one should also have extensionality conditions on the types, and they look like this. And also even here, the coercions enter. Okay. So this this is. You can use this to get some kind of syntax for an extensional type theory, but it's of course just extending the judgments we had before to those. But it's of course a bit unsatisfactory that you have these coercion appearing here. On the other hand, they are not complicated; they are always unique and so on. So so the question is, can we now construct a model of a Setoid model in this framework? And I will talk about some work in progress here. So what about the internal models? So I mentioned the difficulty of constructing categories of Setoids, and and also to construct this. The context category will encounter similar difficulty because it must be closed under pi and sigma and so on. So one possibility is to make a reconstruction of a Setoid universe, and this is what we have done. So we have so a graded universe. So it's a family of Setoids which has a grading function. You can lift a code from one level to another, and so the purpose of this grading is to limit the constructions of pi and sigma. So you can do pi and sigma from one level to the next in this grading.
So what is graded? The universe or each Setoid family?
Oh, sorry. A graded universe is a family with this grading. So what is the problem?
Okay, so each family.
No, a graded universe is some particular family of Setoids with a grading function. Okay, so we are constructing a universe of sets or Setoids which is powerful than the